Alright, so what's so important about mud?
Mud is all over the earth. All the oceans, you can find mud. And it's great because it is stacked up in chronological order, with the youngest being on top and the oldest being on the bottom. You can stick in a tube into the mud, pull it out, have it oriented, and measure the magnetic field on the mud.
Alright, so that lets you find magnetic fields from how old? How long ago?
Well, the ocean mud goes back to 200 million years. So we can, in theory, find the magnetic fields up to 200 million years ago just by using mud.
As bits of sediment float down to the ocean floor, they stick to other detritus, making larger conglomerates called flocks. Small particles of magnetite or other natural magnets in each flock weakly magnetize it, so that as they fall, the flocks tend to align themselves with the ambient magnetic field. Worms like this one eat their way into the sediment on the ocean floor to get organic material. When they poop, the fecal pellets realign with the ambient field. Other seafloor creatures also disturb the sediments, but each time they're disturbed, they realign with the field as they fall back down. As more sediment falls, lower layers become compacted, lose water, and become fixed in place.
At first, it's going to measure the sample holder, that's this thing, to see how strongly magnetized this is. This is very weakly magnetized, almost no magnetic field, but it does have some. So I need to measure that so I can cancel it out later.
Okay.
So I put it down into Bubba, and I measure it. And it's measured.
That's quick.
Very quick. That's why this is a great thing to do, and very easy to do. So now I pull it back up, and I'm going to take my sample and put my sample in Bubba.
Okay.
And I'm going to orient it in line with Bubba. Now I'm going to lower the sample into Bubba. And measure different locations. At 0, then I'm going to rotate 90 degrees. Rotate 90 degrees more. And again. And so now I've covered 90 degrees around the circle, and the whole circle. So now I bring it up. And I'm going to measure a baseline. What the magnetic field is in Bubba without anything in there.
Okay.
And that's how I measure the sample and its magnetization.
The sensor in a cryogenic magnetometer like Bubba is a squid, or superconducting quantum device. The pickup coil is a wire of superconducting material, like niobium, that is cooled by liquid helium so that it can superconduct. When a sample moves through the coil, it induces a current in the wire. At the Josephson junction, however, the wire is thinner, so it can't carry as much current as the superconducting wire on either side. When the current is greater than what the Josephson junction can handle, the entire circuit stops superconducting. As soon as it stops superconducting, however, the junction stops being a barrier, so the circuit resumes superconducting. How much the circuit flickers back and forth can be measured and is proportional to the sample's magnetic flux, so researchers can deduce the strength of the magnet. By having multiple devices at different orientations, researchers can also determine the direction of the sample's magnetization.